Hi everyone, my name is Ashley Bedford and welcome back to the Runtime Diaries. I am super excited about showing you day 2's coding challenge from Educative's hashtag 30 Days of Code Challenge. I'm going to be breaking this one down for you in plain and simple terms, and I hope you enjoy it. Let's get into it. Today, we're breaking down a deceptively simple problem. Maximum number of integers to choose from a range 1. On the surface, it's just about picking numbers, but beneath it, this challenge tests how efficiently we can filter, track, and sum values, all while respecting a set of invisible boundaries. Now here's what the problem says in plain English. Imagine you have a list of numbers from 1 to n, kind of like a shelf filled with boxes labeled 1 through n. But some boxes are banned. Maybe they're locked, broken, or just off limits. You're allowed to pick as many boxes as you want, but there's a catch. The total sum of numbers you pick cannot go above a certain limit called max sum. Your goal is simple. Find out how many boxes you can collect without breaking the sum rule or touching any banned ones. That's it. Simple in theory, but in practice, it tests how well you can translate constraints into efficient logic. Let's walk through a quick example. So let's say our band array from left to right is 1, 6, 5, and our n value is 5, and our max sum value is 6. The valid boxes you can pick from are from left to right, 2, 3, and 4. You can start adding. So 2 plus 3 is going to equal 5. If you try to add 4, the sum jumps to 9, which breaks the limit. Our limit is going to be the max sum, which is 6. So you stop right there. The maximum number of boxes you can pick is 2. Let's try another example. Band equals from left to right, 2, 3. N equals 5, and max sum equals 10. You can take from left to right 1, 4, 5, and 1 plus 4 plus 5 equals 10 exactly. And that's 3 valid picks. So this problem isn't about finding which ones, it's about counting how many you can take before crossing the sum boundary. So what pattern are we really solving here? Think of your array like a circular board. You move from 1 up to n, checking each position. If it's not banned, you ask, can I afford this number without going over budget? If yes, you take it. If no, you stop immediately. The key here is not overthinking. We're just filtering out the banned numbers, then accumulating a running sum until we hit the wall. Once run sum plus x exceeds your max sum, we break. The difference between a clean solution and a clunky one comes down to how you track what's banned and when you stop. Let's start with the brute force approach, or as I like to call it, the let's just make it work version. We'll begin by creating a set called my_set that holds all the banned values within range. Then we loop through every number from 1 to n. If it's banned, skip it. Otherwise, check if adding it keeps us under the max sum. If yes, add it to our running total and increase our count. Easy. It runs fine, but there's something subtle happening here. We're doing unnecessary work, removing and re-adding elements in the set even though it doesn't affect the end result. It's like writing names on sticky notes for banned boxes, then ripping them off and sticking them back on every few seconds. It works, but it's not efficient. So what's the cost of doing all that? Well, for our naive approach, we have a time complexity of O of n, since we loop through all the numbers once. Our space complexity is O of m, where m is the number of band numbers. The big inefficiency here isn't in complexity. It's actually in our operations. So every unnecessary set removal or re-add creates friction. And in competitive programming, that friction does add up. So we can do better. Enter the optimized version. The core idea is the same, but we strip away everything we don't need. Instead of juggling sets back and forth, we create a clean set comprehension for the band numbers. So in this code, we can see brackets, and inside the brackets, B for B in band if 1 is less than or equal to B, which is less than or equal to N. This ensures we only store values that actually exist in our range. Then we use a small but powerful trick. We bind the underscore contains underscore method of the set once to a variable, so each lookup runs faster. It's like instead of checking the sticky note board every time, you keep a quick mental list of what's banned, instantly available and accessible to you. So here's what the optimized code looks like. Take a second to look at it, inspect it. It's simple, it's elegant, and readable. Each part does exactly one thing. There is no redundant logic, and there's no clutter. So what did we gain here? Well, for the time complexity, it's still O of n, but the constant factors drop dramatically because we break early once our sum exceeds the limit. Many cases stop long before reaching n. And then our space complexity, O of m, just enough to store the band values. The biggest win is practical here. This code runs smoother, cleaner, and leaves less mental overhead when reading it later. Here's what the problem teaches you beyond syntax. First, always filter your inputs. Don't waste time tracking values that will never matter. Second, binding or caching small operations like band underscore set dot underscore contains underscore can make your loops run significantly faster. And third, early stopping conditions are your friend. Optimization here isn't just about math, it's about intention. It's knowing when to stop, not just how to go faster. Let's talk about what not to do. 1. Forgetting to filter your band numbers beyond the range of n. That's wasted memory. Number 2, forgetting the break. You'll keep looping even after you've already hit the max sum. We don't want that. And number 3, using unnecessary operations like .remove and .add. They only add noise. The best code isn't just correct, but it's quiet. It does its job and doesn't ask for attention. So let's recap together. The naive solution worked, but the optimized one worked smarter. We simplified our logic, reduced redundant steps, and improved runtime efficiency by focusing on clean flow. Remember, solving problems isn't about flexing complex syntax. It's about writing code that thinks clearly. Just like organizing your room. First, remove what doesn't belong, then keep what adds value. And that's exactly what this optimization did. And that's a wrap for day 2. Thank you so much for joining us. We've covered filtering, set operations, and even intentional optimization. Those are foundational topics that you need to know in any interviewing type of question and setting. So if you like this video, please like it, share it, subscribe to our channel. We are going to be doing a lot more videos like this for the hashtag 30 Days of Code Challenge with Educative. And if you like Educative's platform, if you like what they're doing, go ahead and check out the link below. I have linked my special code that you can get an additional 10% off of any of their products. Thank you so much, and I'll see you tomorrow. This is Ashley Bedford signing out with the Runtime Diaries.